In this video, we're going to verify the energetic balance. So in order to do that, we're going to have to find, just like I said a few videos before, we're going to have to find all the power generated and all the power absorbed. And then we're going to have to verify that those two values are equal. So let's just do that. As always, let's draw our circuit. So our circuit this time looks something like this. We have a voltage source, which we're going to call V1. We have a current source pointing up, which we're going to call J1. Then we have a node. I'm going to have the opposite side, another current source, which we're going to call J3, and another voltage source, which we're going to call V3. There we go. And here in the middle, we're basically going to have a resistance, which we're going to call R2. This is going to be my point A, this is going to be my point B. And I'm going to call the current flowing here, I2. So this time the problem is saying for the circuit below, we know that V1 is equal to 12 volt, V3 is equal to 6 volt, J1 is equal to 2 amps, J3 is equal to 4 amps, R2 is equal to 6 ohm. Find all the power and verify the energetic balance load. So basically the energetic balance, so how the load is, whether the load is, whether there is the generated powers are more or less than the absorbed power, but essentially those one are going to be equal. So okay, so we basically got to verify and demonstrate that those two are equal. So first thing first, we should write our action plan. Like when you go to war. Yeah, we are in war. This is a war against circuit. No, I'm just joking. Anyway, our action plan. Well, in order to verify the energetic balance, so the load, which is asked by the problem, we gotta calculate the power generated, which I'm gonna call PG, and the power absorbed, PA, from each element of the circuit, and then I'm basically gonna verify that those two are gonna be equal. So I'm gonna find the power generated, which I'm gonna call PG, and the power absorbed, which you're going to call PA, from, well, by each element of the circuit, and I'm gonna verify that those two are equal. So there's gonna be essentially the same. So how do we do that? Well, there is a reason why I said that this one is gonna be called A and this one is gonna be called B. And perhaps you are already thinking about it, but I'm gonna say explicitly anyway. We're gonna apply the Kirchhoff current law to the node A. So as I always do, I'm gonna circle this one in green, just like that. I'm gonna say, okay, I'm gonna apply the Kirchhoff current law to node A. So the Kirchhoff current law. Kirchhoff current law basically says that the sum of all the currents entering a node is equal to the sum of all the current leaving that node. Which we can also say that all the current meeting at a node, the sum of all the current meeting at a node is 0, but anyway. So what are the currents entering this node? And what are the currents leaving that node? Well, it's pretty simple. We have J1 entering the node, we have J3 entering the node, and we have I2 leaving that node. So we know that J1 plus J3 is going to be equal to I2. So the sum of those entering the node is going to be equal to the sum of the one leaving the node. Just I2 is leaving the node, so J1 plus J3 equal to I2. So we can just say that I2 is equal to J1 plus J3. So now if I just substitute those values here, I get that I2 is actually J1. Oh, yeah, I didn't write them in the circuit. I should always do that. I don't know why I forgot to do that, because otherwise I'm gonna have to look up here all the time, and I don't know, it's a bit annoying. Okay, so V1 is 12 volts, V3 is 6 volt, J1 is 2 amps, J3 is 4 amps, R2 is 6 ohm. Okay, so I2 is J1 plus J3, so J1 is 2 amps, and J3 is 4 amps, so it's essentially 2 plus 4. So I2 is actually 6 amps. Now, we have I2. What about it? You may think, well, what about it? Yeah, no. Actually, I2 is actually important because now I can just calculate the power of R2. So I can say, okay, now I have I2, so the power of R2 is actually going to be given by the resistance, so R2 times I2 squared. Okay, this is Ohm third law. Ohm third law. P equal R times I squared. So PR2, we just substitute. We know that R2 is 6 ohm. I2, we just found I2 is 6 squared. PR2 will be 6 times 36. So PR2 is going to be 216 watts. Are those aggregated? No, they are absorbed. Is the resistance. is a passive element. This is the, well, you can't you can't really, say anything about this one. It's the only passive element of the whole circuit. So yeah, you gotta have a passive element anyway in order to verify the energetic balance. So yeah, I'm gonna write sort. Okay. So now we're done with the passive element. That was quick. Let's go home. No. Uh, yeah, it was an energetic balance. We have 216 watts here, so the derogate is going to be 160 watts. That's it. No, we really got to verify it. We know that it's going to be 260 watts, but we really have to verify it. So in order to find all the active element, the power for all the active element, and then verify, we're gonna do this. First, I'm gonna try to find the voltage on the generator J1. So the voltage of the generator J1. So I'm basically going to find this VAB. So VAB will be R2 times I2. Okay, makes sense. We have two ends, A and B. So the voltage here, right now, is going to be basically the resistance times the current, which I've just found. So if we plug numbers into this, we're going to have R2, which is finite, is 6 ohm. And we also have I2, which we just found is 6. So 6 times 6, VAB, which is going to be 36 volts. Now, I can say, okay, so we know if we consider, why have I done this? Well, because now, since I have the voltage here, I can say, okay, I'm just going to consider this mesh. And this is indeed a mesh and is also closed loop. So, basically because it's a mesh. So it's a mesh, it's a closed loop. I can basically say I'm happy because I can say that V1 plus VJ1 minus VAB is going to be equal to 0. Therefore, since we are interested in VJ1 really, because we know the other two, we can say that VJ1 is going to be VAB minus V1. So VJ1 is just going to be, if we plug number back into this, VAB, which is 36 volts, minus V1, which is 12 volts. So VJ1 is 36 minus 12, which gives me 24 volts. Now I can finally find the power on J1, the power erogated by this current generator, which I'm going to call PJ1. So PJ1, yeah, by the way, PJ1 is on like PJ1, but I don't mean one PJ. I mean the power erogated by the generator J1. Yeah, I shouldn't really be making those jokes, honestly. Anyway, so the power generated by the generator J1, which I'm going to call PJ1, and it has nothing to do with birds, is going to be VJ1, so the voltage times the current. The voltage on J1 times the current. So I can say that PJ1 is 24 times 2, which was 2 amps. So 24 times 2, PJ1 is 48 watts generated. Okay, we're getting closer. Now I'm gonna find the voltage on the generator J3. So, well, I can just say, okay, fair enough. VAB minus VJ3 minus V3 is equal to 0. Must be equal to 0. I'm just considering these other mesh, these other closed loop here, just like before. V1. So VAB minus VJ3 minus V3 equal to 0. So since we're interested in VJ3, we can say that VJ3 is going to be equal to VAB minus V3. But then VJ3 is VAB, which we just found before, is 36 volts minus V3. V3 is finite, so it's 6 volts. So VJ3, 36 minus 6 is just 30 volts. Now I can just calculate the power on J3. So the power on J3, that's loosely speaking, power generated by J3 actually. So the power generated by J3 is just going to be VJ3, so the voltage on J3, which we have just found, times J3, so the current, times J3, the current. Just like I did before for PJ1, but this time I'm going to do it for PJ3. Pretty straightforward, as I said. So PJ3, VJ3 was 30 volts times 4 amps. Voltage times the current is going to give me the power. So 30 times 4 is just 120 watts generated. Erogated, generated, whatever you want to call it. It just, goes out. So, I know what you're thinking. You're saying, okay, but we have 120 plus 48. This doesn't actually, is not equal to 216. There's something missing here. Of course there is. We have just calculated this on the current generator. We gotta make sure we gotta calculate this on the voltage generator as well, of course. So PV1, so this voltage generator here, the power generated by this voltage generator here is just V1 times J1. So if I plug number back into this, I can get that PV1 is 12 times J1, so times 2. So 12 times PV1 is 12 times 2 is 24 watts. Again, generated, erogated, whatever. And then we know that PV3, okay, so PV3, and the very bottom of the page, but I don't want to change page now, we are almost there. But PV3, okay, which is this one, and the power generated by this voltage generator here, just going to be V3 times J3. So PV3 is 6 times 4, which is just 24 watts generated. Okay, so now we're basically there, because we're basically done. All we need to do now is just to verify the load. So we're gonna say, okay, let's see, is 24 plus 24 plus 120 plus 48 equal to 216? Yes, it is. Yes, it is. So we're basically saying that I'm just gonna make Just gonna write here, don't want to change page for just that. So we're basically saying, okay, so pj1 plus pj3 plus pv1 plus pv3 is equal to pr2. Is it equal? Of course it is, because it's 20 is where it is? Yeah, no, is where is it? Oh, okay. pj1 is 48 plus 120 plus 24 plus 24. Is it equal to 216? Well, yeah, sure. 120 plus 24 plus 24 plus 48. Yeah, this is 216 equal to 260. There we go. We have verified the. I'm gonna draw a little box here like mathematicians do. We have just verified the energetic balance, the energetic law, they're basically equal. The power generated and the power absorbed, so the power erogated and the power absorbed are actually equal. So yeah, that is pretty much it.